In the previous example, we showed how we can represent the force that propels a person forward or makes a person walk forward is actually that interaction between the foot and a surface, and it results in a static friction force pushing the person forward, right? Preventing that slippage of the foot. So this is part of what we call propulsion. So propulsion is going to be a force where we have a system and it's got some internal source of energy that's going to drive that object forward. So we're not going to focus on the details of the internal source of energy and that working. That's going to be an internal to our system. But we do want to talk about, I've got 3 different cases here where I just want to show and highlight how we come up with the force that is going to do that propelling forward, right? And so to do this, the thing we want to make sure and be careful of and focus on is this agent and object idea. So thinking about our forces, thinking about third law, right? So sometimes it's easier to think about what our object is doing to the other object or to the surface, and that helps us kind of backtrack and figure out how the surface is interacting with our object, which is usually the force that we're interested in. So if we go back to that idea of somebody just walking, right? So if somebody is walking, we are really interested in this little interaction here. So the contact between the foot and the surface. And so again, we can kind of think about this from both objects' perspective. If we think about it from the surface perspective, right? If this is my surface, the foot is pushing to the right against the surface, right? This foot is pushing back this way. So from the surface perspective, I can have the force of the foot on the surface. From the foot's perspective, so if we think about the foot perspective, the surface is pushing forward on that. And so a couple of ways you can think about it. I always like to think about it as if there was no friction there, the foot would be sliding it back against the surface, right? There would be slippage and the foot would slide this way. So the friction is preventing that foot from sliding. So the friction that's preventing that sliding to the left has to be a force, a friction force that's pointing to the right. So this force here, and we're going to call this a static force again, because that foot is not slipping. So if the foot was slipping relative to the surface, that would be kinetic friction, but it's not. So it's not slipping. So at that exact point, this is a static friction. So this is the force of the surface on the foot. Okay. So we can think about that from the context of that static friction force is preventing the slippage, or also we know that this force on the foot has to be equal and opposite of the force of the foot on the surface because these are action reaction pairs. We can do the same sort of idea if we have a car. So if a car has an engine, there's going to be some internal mechanism where that energy from the engine is going to result in the wheels spinning, right? The drive wheels spinning. So if we think about this contact point of the tire with the surface, the same sort of thing. So if there was slippage, then the car would be slipping back or pushing this way, right? So it would not be able to propel forward if there was no friction. The tires would just spin in place. So if we think about what has to be making the car propel forward, just like with the foot, there has to be something here that is pushing back on that tire. So as the tire pushes this way, there has to be the surface pushing back in the opposite direction. So the friction force here again is going to be a static friction force, and that is going to be the force that is actually going to cause that car to accelerate or propel in the forward direction. We also have another case you might see this propulsion force is in a rocket engine that's maybe launching a rocket. So in this case, we're going to have the rocket has some sort of internal combustion explosion that is going to happen, and that rocket's going to push the hot gases backward, right? So here from the rocket, we're having a push of all the gases, the air particles beneath the rocket are going to get pushed back. And that means if we think about third law, there has to be an equal and opposite force that's pushing upward in that opposite direction. And that is going to be our thrust force. So these are just different examples of propulsion. And so this is, I guess I want to mention also here, this one where the car is has that internal engine going, right? Or there's something accelerating that car forward. This is different from our rolling friction. So rolling friction could be if you have a cart and you've got some wheels here, right? And this little cart is just getting pulled along. So there's no internal source of energy propelling that cart forward. This is what we're talking about when we're talking about rolling friction. So rolling friction is not propelling the object forward. The friction that we're talking about here, that propulsion friction, is resulting if I have some sort of internal engine that is driving those wheels forward. So just want to make a little distinction between that. So this case is going to be static friction. This would be our rolling friction, and that rolling friction would oppose the overall motion of our object. Okay, let's do another example here where we're going to go through an interaction diagram. And so I've got a tow truck pulling a car, and then we also have a rope. And in this case, I'm going to talk about each of the objects, so including the rope. So I'm going to make an interaction diagram. We've got the car, the rope, and the truck. The car and the truck are contacting with a surface, and then we have the entire earth, which is everything is going to be interacting with. Okay, so I'm going to do my earth interactions. So the car, the rope, and the truck are all going to be interacting with the earth. They're all going to have their own gravitational forces. The truck is going to have those interactions with the surface, and I'm going to put two, right? So one will be a normal, one will be a friction. The car is going to interact with the surface. We're going to have a normal and a friction. The rope is not interacting with the surface, so the rope's not contacting the surface, right? It's kind of suspended there above the surface. The car is interacting with the rope, and the rope is interacting with the truck. So we are going to define our system here. So I'm going to say the system is the car, the rope, and the truck. I'm going to use a different color here. So we'll do this color. So we'll use this to indicate this is going to be our system. So we're going to do free body diagrams for 3 different objects here. So we'll do one for the car, one for the rope, and then one for the truck. So let's go ahead and identify those. So here's my car, here's the rope, and here is the truck. So we've got each of those labeled. So first I'll just do each of these objects has a gravitational force. So we're going to just label this mass car G. This one will be mass rope G, and this one will be mass truck G. And remember, we do need to specify those different masses because the objects will have different gravitational forces. They have different masses. Okay, so that takes care of. I'll just check these off in orange. So I took care of those forces there. Then we also have interactions between the car and the surface. So we'll do that one first. And so the car is just getting dragged along, right? So the car, the wheels are just going to be rolling or sliding. Actually, they're probably going to be rolling. So I don't think it's a good idea to drag a car with wheels locked. So the wheels are going to be rolling, but there's no internal source of energy in the car, right? So if we think about those interaction forces between the car and the surface, we'll have a normal, and we'll have a friction. So if the whole thing is moving this way, then we're going to have some rolling friction. I'll say rolling friction on the car that is opposing that motion. So we're going to have that force. That way. Okay, so that takes care of these two guys. I'm going to hold off on the rope for just a second. So let's go ahead and look at the truck and the surface. And so for the truck and the surface, we're going to have normal force, of course. And this is normal of the truck. And then this one, the friction. So the truck is going to have an internal source of energy, right? So there's going to be an engine and the truck is doing the pulling. So there's going to be some force that is turning those wheels. And so this is just like that propulsion that we talked about in the previous example. So I'm going to just say that this is a friction, and this is going to be a static friction of the truck, right? That's going to be a thing that's going to propel that a truck in basically the whole system forward. Okay, so now we have the interactions between the car and the truck, and so I'm gonna and the rope. So I'm gonna start by just looking at the rope. So these are going to be our third law, right? We want to recognize these are the forces that are internal to our system, so they're going to show up in multiple diagrams here. So let's take these from the perspective of the rope, because the rope is interacting with both of these. So we may be tempted to do this and draw these forces and say this is the force of the truck on the rope and this is the force of the car on the rope, right? Because it looks like in the picture that's kind of what's going on. But if we do this, we want to be careful. So if we do this, we should recognize that there's no force in the upward direction, right? So if we draw our forces between the rope and the truck and the rope and the car horizontally, then there's no force in the y direction. And then that would result in this rope accelerating downward. And so that's not our experience. So that's not what would happen if the truck is pulling the car, right? There would not be, we do not want there to be acceleration in the y direction. And so we need to adjust this a little bit. And so for the that force, and this is going to be a tension force, right? So that force here needs to be a tension of the truck on the rope. And then here, tension of the truck on our car on the rope on this side. So if we do this, right? If we do this, then we do have that little bit of a upward component of those tensions that can balance out that gravitational force. And so if you, I mean, in the picture, they kind of drew this a little bit here, but you could probably imagine that you could kind of see that a little bit as well, right? So if we're really keeping track of the forces on that rope, then there would be some upward bowing of the rope or the chain to ensure that the chain itself is not accelerating downward. So if these are our forces here, then that is going to allow us to do our force of so this is going to be the tension of the rope on the car. And then over here, this one is going to be our tension of the rope on the truck, right? And these guys are going to be action reaction pairs here. So this is an action reaction pair and this is an action reaction pair. So those are our internal interactions, our internal forces to the system. So we have these three different objects. We know that these action reaction pairs, so I'm going to write these down here because this part of what we want to do when we have a diagram like this is identify these action reaction pairs. We're going to say that the tension R on the car is equal to negative tension car on the R, which is the rope. And then we also have tension of the rope on the truck is equal and opposite to tension of truck on the rope. So you'll see that when we're doing some of these interactions, it gets really messy quickly. And so it's easy to make little mistakes on our notation here. So hopefully you've been kind of focusing on this up to this point through this semester and really focusing on being very deliberate and intentional about your notation and your labels. And that will help you immensely as we then, so in this problem, this is all we're doing is drawing this out. But in future problems, then we're going to start identifying these forces or thinking about the acceleration of the system, right? So we're going to need to apply our equations to these diagrams. And so the better and more efficiently and more concisely, I guess, we're labeling our forces, the easier it's going to be when it comes to plugging those things into equations.